Hey, Mr. J here with another video lesson for us. Um, Jumping into our new curriculum, the Houghton Mifflin Harcourt. I hope you were able to log into the website using your email, and password 1 is your password for now. And we may change that later. But I think our textbook's really good. I'm getting used to it myself. But we'll be complementing it, as you'll see in today's lesson, with other sources and other technologies to hopefully make it more than just a video. And then I want you to participate in this as well. So, do you know what this is behind me? Do you guys recognize this type of drawing? It's very geometrical. Do you see anything interesting about it? This is done by a Dutch illustrator with no formal training named MC Escher, and I love his work, his optical illusions. And can you see the birds here? The white birds going to the right and the black birds going to the left, and how it fills the plane. And plane is one of our terms from today. A plane is an infinite two-dimensional surface, and we'll talk about points, lines, and planes today as a means of introduction. But I want to go right now over to our textbook. See if you can see this. I need to make it a little bit smaller. Okay. Textbook set up well, where it gives you some basic information on the left page here of what you should know. Are you ready as we begin? And then it jumps right in. And I didn't find this first page to be great, but what mathematical terms can you see in this picture here? Can I zoom in a little bit more here? Well, I can scroll a little bit. So you can read through this. I'm not going to do that for this one right now. I want to move ahead to the next page here and talk about something called undefined terms. And I find this really interesting that we are going to define undefined terms, and that just seems odd to me. Isn't that a bit odd? Why would we define undefined terms? So we have 3 of them here. Undefined terms: a point and what that means. A point has no dimension. It names a location in space, in this case 2-dimensional space. A line is a straight line path of points in a plane, has no width or thickness, and it continues forever, and we draw them this way. You should be noting a little bit here, capital letters here for C, D, and E. Line AB or line L, and down here a plane is a flat surface, has no thickness, and it extends forever, and you can see that it's drawn with a parallelogram. And we could call it plane ABC, or we could do a little italicized R up in the corner here, and that would indicate that. But I haven't answered the question for you of why we have undefined terms. And I think that's pretty important. So important that I'm going to introduce you to a friend of mine. I've already mentioned him in class, and his name is Dr. Tanton. And I think his explanation is really good here. So let's go to a quick video by Dr. Tanton about why we define undefined terms, or why we have undefined terms.
So, I've never actually said so far what a point or a line actually is. All I have done is given some notation for it. We said points will be labeled with capital letters. I never said what a point is. I never said what a line is or a line segment is. So we like to believe that we start a subject, it'll be good and proper to start with a list of unambiguous beginning definitions. But the trouble is, every definition uses words. And those words, at the beginning of a subject, would also need to be defined. We'll be caught in circular reasoning. For example, this example on the board right now. Suppose I didn't know what the word dog was. So I go to my dictionary and look up dog, and I see a dog is a canine. Well, that's grand, except I don't know what canine means. So I go to the dictionary again and look up canine. It says a canine is a dog. Not very helpful. I'm stuck in a circle of reasoning. There's no actually way for me to get a sense of what a dog or a canine actually is. Now, it's hard for us to understand this problem here, the problem with this, because I actually do know what a dog is. I do know what a canine is. So let me give you an example that's extremely silly, but I want to make the point that circular reasoning is a serious, serious problem. Suppose I told you that a waglet is a possum with flattles. You have no idea what I'm talking about. It's nonsense. So you looked up waglet and you said it's a possum with flattles. So I'm going to have to look up the word postum because I have no idea what a postum is. All right? My dictionary says a postum is a flatterly oglet. Uh-oh. What's an oglet? An oglet is a waglet, either with or without flattles. Oh, flattles. Have you looked at the word flattles yet? What's a flattle? A flattle is what postums have. All I'm going to say is, huh? That's a line of 4 definitions that are so tangled within themselves, there's no starting place. I have no idea after reading that what is a waglet, what a postum is, what an oglet is, what a flattle is. Useless. So here's my point. The start of geometry suffers exactly the same problem. One cannot escape circular reasoning. So, since we cannot escape the circular cyclic of reasoning for definitions, scholars have agreed that some beginning words must remain undefined. Point, line, plane, straight, and so on. In fact, these are called undefined terms.
So I think that's a really good explanation on why we have undefined terms, right? Does that make sense to you that we have to start somewhere and then accept these to be true and we'll call them undefined because otherwise we'd have to go look with, what does straight mean? Or what does point mean? And we go to point and then it has location. Then we have to go define what location is and dimension. And instead, we're just going to say this is our starting point, okay? Some other words here. Endpoint is at the end of a segment. Let's be really careful in how we use terms like line and segment. Line goes on infinitely, and segment is made of endpoints and has a length, okay? This is a line segment down here, or just a segment. You don't even need the word line. And indicated here, AB with this bar on top of it. And rays have a starting point, say H, and goes through I. And you can look at these questions here. But I wanted to move ahead a little bit. I wanted you to know about a postulate. And a postulate is they're rules that are accepted to be true without a proof. Okay, no proof is necessary, but we'll see some postulates. And postulates are going to seem pretty basic. We'll have maybe a dozen or 13 postulates that are very basic rules. Segment addition postulate. This hopefully will make sense to you. If I have a distance between AB and a distance from BC, then the distance from A to C is the sum of AB plus BC. Okay, and we could do this with a straight edge and compass, and maybe that'll be something we do in class. Another thing I want to do in class is how to bisect a segment, a really important skill that we will do on paper. But right now I'm just going to demonstrate how we would do this in my favorite software, one of my favorite softwares, something called Geogebra. So Geogebra is free and open source, and you can get to it by just doing Geogebra and do classic. I like the classic version, and you can get right there. And then typically we will be going to the geometry version. And now we have some tools in our top left that we can use, and I want to show you how we bisect a segment. So here's a segment. It has a length. We could actually measure the length by clicking in here and finding the distance or length. It will tell us that 9.78 somethings. I don't know what those somethings are, 9.78 somethings. And now what we're going to do is we're going to use a compass, a digital compass. So here's a compass. And do you see how it has a red circle and then this little segment below it? That is what I call the radius tool. So before I click on a compass, I'm going to put the radius tool up here. This will allow me to set the size of the circle, and you'll see how this works. We'll do this frequently. So I just clicked on compass. You can see it's highlighted. I'll click on here, and now this circle has that radius, and I can put it here. Okay, and what's neat is if I change the radius, the circle changes size. And the other thing that's neat is that I can make another circle with that same radius down here. So both of these circles have the same radius. And what I want to do is figure out, I want them to meet. I want them to intersect. So I'll go to here. So they are more than halfway, and they have the same radius. And now I can find the intersection of these two circles. There's the intersect tool of this circle and this circle. And if I draw a line, I'm going to do a line and not a segment between these two. This line here, and I'll change its color, is called a perpendicular bisector to the original segment. So this is the original segment, right? AB, which had a length of 9.52. By drawing these circles, we can do it on paper with a compass, physical compass, but we probably won't do that this year because we don't want to do a lot of handheld manipulatives. That's why these digital ones are great. And it identifies, let's find the intersection now, the midpoint of segment AB, and it uses a G here. Let's find the length here. It should tell us that AG is half and BG is half, and so this is the bisecting segment. And it's actually a perpendicular bisector, and so we can see that perpendicular meaning 90 degrees, that it does meet at 90 degrees. And I love this dynamic software because it allows me to change the length of that original segment, and if we construct it correctly, the red line will split it right in half. So if it becomes too far apart, that segment's too long, what I can do is extend the radius until they meet again, and it still knows what to do. So now we're at 17.59, half of which is 8.79, off a little bit by rounding. All right, so I think that's a really good tool. We have one more thing here today, which is how to find the midpoint of a segment. And let's go back to Geogebra. Let's do this again. Geogebra Classic, reload, so I'm going to get another blank page. This time I'm going to do graphing more like Desmos, maybe, if you're familiar with Desmos. And if I go ahead and put a segment in here, and let's go over to, say here, a segment, and we can see the coordinates here, -3, 3, and 11, 7. That's where A and B is. It gives me a length here, which we'll talk about the length, how we might calculate that, but it gave it to me. And I want to find the midpoint. Where is the middle here? And I think we could kind of guess at it, that it's got to be maybe right here. Doesn't it look like it? Well, I don't like to go with looks like it. It's how do we calculate it? And what you want to know about midpoint is that it's the average. What is the average of the x values? -3 plus 11 is 8. And you divide it by 2 to find average, we get 4. So on the x-axis, 4 looks right. Okay. On the y-axis, 3 plus 7 is 10. Half of 10 is 5. Right, so that's halfway here. Right, up 2, up 2. So it's up 4 total, half is up 2. Over here we went over 14 to go from -3 to 11. That's 14. Half of that is up 7, and that's why we're right here. So yes, this is the midpoint there. And if you want to confirm it, lots of tools built into Geogebra. There's a thing called midpoint. And if I just click on this segment, it tells us the midpoint is right there at 4, 5. All right, so here's the algebraic version of this, where it looks complicated. It really isn't. It's just saying add the x values and divide by 2, add the y values and divide by 2. So you guys are going to have some homework here to work on. And please remember that homeworks are going to be put into the mathematics folder, right? So your first assignment was that algebra, the geometry readiness, the algebra review, and that was homework 1A. This will be homework 1B. It needs to be done by hand, probably, and then scanned and put into your mathematics folder. So I hope that's helpful. That's the end of lesson 2. We are at 14 minutes here. All right. Be in touch. Send me emails. Check out MC Escher and check out Dr. Tanton. You can find a lot of his videos online.